All right, guys, we're ready to get into the math of chapter 4. We are on slide 13 of the PowerPoint. So we're introducing the idea of molarity. Very important concept. Essentially, when we look at a solution, okay? So you go to lab and there's a bottle on the counter that, whether it's a plastic or glass bottle, the label on the bottle is always going to tell you the identity of what's in the bottle, and the number that's given, it represents the concentration. Okay. Now the idea of concentration is really important because essentially every time we deal with different types of samples, sometimes the way we have to assess or measure what we have is going to vary based upon the physical state. Okay. If I have a piece of gold and you ask me, how much gold do you have? As a chemist, or just most people would say, well, let me go weigh it, and I would put it on a balance and weigh the gold and say, oh, I have 5 grams of gold, or whatever it is. Okay. Anytime I have a solid or a pure liquid, then I can weigh it. If I say go get 50 grams of water, you could get a container, pour in water until it's 50 grams, and get it that way. Okay. But you also, knowing the density of the water, you could that 1 milliliter of water is about 1 gram. So you could go get 50 grams of water, 50 milliliters of water, and assume that's probably 50 grams also. Okay. So sometimes there's different ways of measuring things based on what you have. Now, when we get to a solution, though, this gets a little bit more complicated. That if I get a bottle of hydrochloric acid solution, and by the way, anytime you get a bottle of an acid in lab, it's never going to be pure acid. It's always going to be that acid dissolved in water. So if you want to assess how much is in there, you can't just go to the balance and weigh the solution. Because when you weigh the solution, that doesn't tell you how much acid's in there. Because usually, most solutions that we make are pretty dilute, which means there's usually a little bit of the solute and there's a whole bunch of the solvent. So if I weigh a solution of hydrochloric acid, the number that I get mostly represents the water that's in there. And it's hard to distinguish how much of it's water and how much of it's acid. Okay, so that's why with solutions, we typically don't weigh them. All right, now, if I say, go get some hydrochloric acid, the way liquids are most commonly measured is you get a volume. Okay, so you get a graduated cylinder, and you could pour a certain amount of the solution into the graduated cylinder, and so, okay, I have 35 milliliters. But that still doesn't actually definitively tell me how much acid's in there. We need 2 values to get the amount of the acid that's in a container of the solution. We need the volume, which is a very important value, but we also need the concentration. Okay, so in chemistry, the most common concentration unit that we use is called molarity. The definition of molarity is it's the number of moles of a solute divided by the liters of solution. Okay, in some ways it's a little bit like density, where if you want to know how much of a sample you have, within a given volume, you have a certain mass. The mass to volume is your density. But density is used if you have a pure substance. When you have a mixture, a given volume of the solution, which has water and HCl in there, it's going to be the moles of the HCl on top and the volume of the solution on the bottom. It gives me a ratio that I can use. If I have 6 molar HCl, what that means is it's 6 moles of HCl per liter. Okay, so I could say if I have 1 liter of that solution, then inside of it there are 6 moles of HCl. If I had 2 liters of that solution, I know it's 6 moles per liter. So if I multiply by 2 liters, again, if you set up your conversions, the liters would cancel. 2 times 6 would give you 12 moles of HCl. So in 2 liters, there'd be 12 moles, because in 1 liter there's 6 moles, and it's just gonna be a constant ratio. If I have a half of a liter, or 500 milliliters, that's gonna be 1 liter has 6 moles, so a half a liter would have 3 moles, because again, that's the same ratio. Okay, So it's just a way of assessing how much of a solute's in solution. In chemistry, we like the unit molarity, because when we do balanced equations, our favorite unit to use with balanced equations is moles. So if we're going to be doing any reactions and stuff, this is our preferred concentration unit. Now, there are other ones that you're going to learn, especially in the first couple of chapters of 1212. First of all, we have to write molarity. If we abbreviate it, it's always a capital M. If you write a lowercase m, that stands for molality, which is the moles of solute per kilogram of solvent. It's a little bit different. It's kind of technicalities and stuff that'll be important in 1212. But for now, just make sure you always put the capital M when you write molarity, not a little m. Okay, and that's when you're abbreviating it. Now, there are other concentration units that are used in everyday life. A common one is percent mass to volume. If you go to the hospital and you are dehydrated, they will give you a saline solution IV. So it'll be sodium chloride in water. The concentration is very important. If you drink ocean water, there's too much salt in there. It actually dehydrates your body more than it helps your body. So that's why people, if they're stuck on a deserted island and there's no fresh water, that's why they usually die of thirst. So the concentration of a saline solution used in a hospital for IV is 0.9% mass to volume. Now what that means is if you had 100 milliliters of that solution, if it's 0.9%, which is the parts out of 100, that would mean it's 0.9 grams of salt per 100 mils of solution. 0.9 over 100, 0.9%. If you get if you can't eat, so you're unconscious in the hospital and they have to put you on a glucose IV, that's gonna be 5% mass to volume. So that means it'd be 5 grams of glucose per 100 mils of solution. All right, so concentration is always going to be the amount of solute over the amount of solution. It's always going to be a ratio, but the units can change. We will work a few problems here and there that have other concentration units like that, but for the most part, in this chapter, we're going to focus on molarity. Okay, so let's stick with that. Now, the real big important thing about molarity, it's going to be my connection I need, that if I measure the volume of a solution, and if I know the molarity, I'm going to use the molarity as a conversion unit to get to the moles of the solute. And again, if we're doing a chemical reaction, we always want to get to moles the quickest way we can. So specifically, it's going to be the volume times the molarity to get the moles. If you will memorize that, it will help you a lot in the future on test 2 and test 3 as we take it. And when you go to 1212 also. So here we have a problem. I have, let's say I take from that bottle on the previous slide, I have 35 milliliters of the solution poured into a graduated cylinder, and I want to know, okay, how much HCl is actually in there. All right, so calculate the number of moles of hydrochloric acid that would be present in 35.0 milliliters of 6.0 molar HCl. Now the picture on the previous slide only had the 6 molar with 1 sig fig. I went ahead and added the 0.0 just to make it a more reasonable problem for us. So our answer, if we're doing multiplying and dividing, is going to be 2 sig figs when we write it. Okay, so pretty simple problem. I have the volume, which is 35.0 milliliters of the HCl solution. I want the moles of HCl. So, first of all, if I'm going to use molarity, it's very important that I remember molarity is supposed to be moles per liter. So, I need to get the volume into liters before I can do anything else. So my milliliters here, I need to convert to liters. Well, that's going to be 1,000 milliliters on the bottom to 1 liter. That makes milliliters cancel. So now I have the liters of HCl, that'd be 0.035 if you calculate it at this point. Then my molarity, it's 6 moles per liter. Again, that's a conversion unit. 6 moles of HCl per liter of solution. I can flip it whichever way I need it to be. So in this problem, I want liters to cancel. So I'm going to leave it in the normal form, 6 moles of HCl on top to 1 liter of solution on the bottom. Liters cancel liters. So basically I need to do my 0.35 divided by 1,000, which I said was 0.035, times 6. And that's going to give me 0.21 moles. So in my graduated cylinder, which has 35 milliliters of the solution in it, and the density is probably about 35, like about 1 gram per milliliter, so that's probably about 35 grams of solution. But the amount of HCl that's in there, because the 35 grams of solution is water and HCl together, but the amount of HCl is actually 0.21 moles. Okay, so that's a usable number that if I'm doing a chemical reaction, I can use that and then go to the mole to mole ratio and keep going through other stuff. Now, next part, what if we have to make a solution? So often in chemistry, when we go to lab, we are told as part of our procedure that we need to make a solution that we can then mix with other stuff to do a reaction. Okay, so it's very important that we do this in a normal semester in lab. One of the labs you have to actually go in and make a solution like this, so this is important. When you do it, you also have to sometimes write procedures. When you write a procedure, it's very important that you use the proper names of the glassware and the equipment that you're using. So pay close attention on this. Again, in lab later, whether it's 1211 or 1212, at some point you're going to have to be able to use these terms properly. So if I want to make, this problem is to make a 1 molar sodium chloride solution, and I'm going to make 1 liter of it. So I need to know the concentration I'm trying to make, and I need to know the volume that I'm trying to make. All right, so if I'm trying to make 1 liter of 1 molar NaCl, basically that means if I'm making a liter, I need to have 1 mole, because 1 mole to 1 liter, that is 1 molar. Okay, so I'm gonna have to weigh out 1 mole of sodium chloride. So you go to a balance, you weigh out your sodium chloride, and then you pour your solid into this glassware. It's called a volumetric flask. When you are making a solution, if you want the concentration to be accurate, you cannot use a beaker, because beakers, as we should have learned in the first lab that we did, the density lab, the volume measurements of a beaker are not very accurate. When we find the density from that one, you probably didn't get very good values for your density. So making a solution in a beaker is a bad idea if you want to be accurate. We also can't use Erlenmeyer flask. Graduated cylinders they're not set up to like mix solids and stuff, so that's not good for making a solution. You just want to measure a liquid in there and pour it out in a grad cylinder. So a volumetric flask is a container. We have different sizes. We have a 100 milliliter volumetric flask, we have a 250 milliliter volumetric flask, we have a 500, we have a full liter size volumetric flask. So I'd get the 1 liter volumetric flask, I'd pour in the 58.5 grams of sodium chloride. Then when I start adding water, you do not add a full liter of water, because you got to remember the solid itself has some volume. When you add the water, if you add a whole liter of it, you're going to be way over the line. Okay? On the volumetric flask, there's only 1 line on the volumetric flask, because this flask is made to deliver a very specific volume, 1 liter. So if I fill it to that line, I had the right amount. So what I'm going to do, I'm going to add half the water or so into the flask. Then I'm going to shake it up until the solid is fully dissolved. Now, anybody that has ever made like protein shakes and stuff like that, if you fill the bottle all the way to the top and then try to shake it to get the solid dissolved, then you probably realize it's hard to shake a bottle that's full, because when you shake it, the stuff doesn't move around very much. Okay? And dissolving the solid is not always an easy thing to do. So you want to add about half to 2/3 of the water. You're going to shake it until the solid has completely dissolved and disappeared into the solution. Once that's done, then you're going to add water up to the line. You don't actually ever have to measure the water at all. Okay? You're just going to add enough water initially to get it dissolved, and then once it's dissolved, then you're going to fill it up to the line. You don't want, there's two reasons to not fill it up right away. Number one, it's hard to get the solid dissolved. Number two, when the solid dissolves, the density of the liquid is going to change, and it's possible if the density decreases as the solid dissolves, then the volume will increase and you'll actually end up with more than you're supposed to, which can affect your results. Okay, so that's our overall procedure for making a solution. It sounds like it's really simple, but there are a lot of details in what I said that are important that you need to follow. Okay, so again, that's gonna be a point where we have to cut off the video, and I'll keep going.